Good morning, everyone. Today, we are going to cover geometric and p-series tests. In our last video, we looked at an introduction into series, and we kind of noticed how we can sometimes guesstimate if series are going to converge or diverge, um, and why they might converge or diverge. And then we had a few different methods of looking at them, but then we kind of came to the conclusion of the um, nth term test. And I said that this test doesn't always work for everything. There's more tests out there that we have to run to see if a series converges or diverges. So today we're going to cover the geometric and p-series test. The geometric series is a series of the form S equals A plus A times R plus AR squared plus AR cubed plus AR to the fourth plus AR to the fifth, and it just keeps on going and going. I wrote this over here for our notes. Because another form would be the summation of n equaling 1 to infinity of AR to the n minus 1. And it converges if the absolute value of R is less than 1. And we know we can find out what it converges to. And it diverges if the absolute value of R is greater than equal to 1. Okay, and we're going to go through quite a few of these tests, and you're probably saying, hey, Katie, how am I going to memorize all of these on our test? At least for our class, guys, you will have your normal formula sheet. However, the second page of your formula sheet will now be the different tests, what the series looks like, and if they converge or diverge. So again, I want to mention that we've already done the divergence test. We looked at a series, and we noticed if the limit as n goes to infinity of that an does not equal 0, it diverges. And that's where we tended to use L'Hopital's a lot. So today we're going to look at two different tests, the geometric and p-series test. It'll be up here on our formula sheet. I'll actually be flipping back and forth to show you how I would use it if I was on a test. Okay. So let's just dive into this. Example 1 says consider the summation of n equaling 1 to infinity of 5 over 2 to the n. Now let's write the first few of these terms out. Okay, so if we let n equal 1, we have 5 divided by 2. And if we let n equal 2, then we have 5 divided by 2 squared, which is 4. And if we let n be 3, we get 5 divided by 8. And if we let n be 4, we get 5 divided by 2 to the fourth, and I do not know what 2 to the fourth is in my head. So I'm going to use my handy dandy calculator. 2 to the fourth, 16. Okay, and so it keeps going and going and going. Now notice that my series, to determine if they converge or diverge, need to have this particular form. A plus A times R times A times R squared. And so, oops, didn't mean to scroll that far. We are going to assume that this first term, this 5 divided by 2, is our A. So A equals 5/2. And then I need to determine what R is. So this is A times R. This one's A times R squared. This is A times R cubed. So we need to kind of figure out what is RR. So what I'm going to do is I'm going to factor the A out because all of these have A's in them. I'm going to show you a different way to do this in a second. This has an A, this has an A, A. They all have A. So I'm going to pull the A out. So I'm going to factor out that, oops, I have to go with black. Oh, pink's fine. 5 divided by 2. And this is 1. So I'm going to start dividing these. Maybe you can do this in your head. I cannot. So 5/4 divided by 5/2. Factoring that out. And I get 1/2. The next one, 5/8 divided by 5/2. And I get 1/4. And I'm going to get next 1/8. And then it's just going to keep going. Okay, so now I have my A. I have my A. And I have my R. Because the second term would be A times R. All right. So A is 5/2. R is 1/2. And so let's go back to our test. I'm just going to flip the page or back to our formula sheet. Geometric series converges if R is less than 1. So let's go back. And our R here is less than 1. So I'm using the geometric series. So the first thing I'm going to do is I'm going to tell my teacher, hey, I'm using this particular test. Just so I can tell if you're doing it correctly. I will take points off if you don't label the test that you are using. Okay. And our R here is 1/2, which is less, the absolute value of it is less than 1. And so that tells me by the geometric series test that it converges. Notice if R, the absolute value of R is less than 1, it converges. So the summation of 5/2 to the n from n equaling 1 to infinity converges. Okay. So for my students, if you're taking the test, when you're ready to give an answer, there's 3 things I'm looking for. You state the test name. So we're using the geometric test, Katie. What is the criteria that it met or didn't meet? R is less than 1. That's all it means. And then what is our conclusion? Three things. Okay. what I do want to do is I want to go on a blank page, and I kind of want to show you guys how I would do this using this particular form. So I'm going to go to a blank page because I ran out of page here. So we had the summation of n equaling 1 to infinity of 5 over 2 to the n. And our test says that our sum needs to look like a times r, that's an r to the n minus 1. And so if I rewrote this summation, we could do some basic algebra on it. And n equaling 1 to infinity, n equaling 1 to infinity. And so I can say this is 5 times 1/2 to the n. So I know that 5 is a constant, so I can kind of pluck it out like I did before when we were listing everything out. But notice the issue is here is that this is to the n minus 1 power, and this is to the n. For these two to be the same, I need this power to be n minus 1. So we can just pull out a 1/2. So as a side note, one half to the n is really 1/2. It's really 1/2 times 1/2 times 1/2 times 1/2. 1/2 times 1/2. And it just keeps going. And there are n of these. If I want there to be only n minus 1 of them, what we can do is say, well, if I exclude 1, if I just look at the back pieces, back halves of them, there is n minus 1 of them. So we do 1/2 times 1/2 to the n minus 1. Oh, that looks a little confusing. Hold on, let me erase my n there. So we group n minus 1 of them, and we break a half. So this is just a side note of what I am doing algebraically. So our summation, going back, n equals 1 to infinity, is 5 times 1/2 times 1/2 to the n minus 1. Just pulling out a 1/2. And so this is summation of n equal 1 to infinity of 5 over 2 times 1/2 to the n minus 1. And so now that we have it in this form, we could then say, okay, this is a geometric series. And it's a geometric series because it has a number raised to a variable power. My A is 5/2. And my R is 1/2. And so R equals 1/2, which is less than 1. So this is step 2. Give me some criteria. Please the more information you give, the better. And 3. So the summation of 5/2 is a 1/2, n minus 1 converges. Okay. So either way we have to do, you can write them out. or you can just work in the summation. I always found it easier to work using the summation. Some people think, or not think, some people find it easier to stretch it out and pull what you need out. And so have your a up front, and then notice that you're having 1 plus your r squared plus your r cubed, and going on like that. Okay. So example 2 says, do you think the following series converges or diverges? Explain. All right. Well, what I notice, the first thing I notice is that there is a numbers, raised to a variable power. So raised to something of the n. This screams, even if it's not the right form yet, geometric. So this screams geometric, 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 use the geometric. So that's what we're going to use here. Okay, so our two forms that we're either looking for is a plus ar plus ar squared plus ar cubed. We can either do that, or we can look at the summation from n equaling 1 to infinity of a times r to the n minus 1 power. Those are the two forms that we can use. Okay, so I like using this particular form, so using the summation notation instead of having it written out. Some people find it easier to write it out. If you find it easier, go ahead and write it out. But let's go ahead and work at this. So we have the summation, n equaling 1 to infinity. And if I'm going to actually leave these off, if there are no bounds, it is assumed n equaling 1 to infinity. Okay, so we have 3 to the n minus 1 over 4 to the n. Well, my top is a number to the n minus 1 power, but the bottom is not. It's just to the n. So let's rewrite this. We have the summation of 3 to the n minus 1. That is fine. But the bottom is 4 to the n, and I need that to be to the n minus 1. So I'm going to rewrite this as 4 times 4 to the n minus 1. So now I can rewrite this. And I'm going to do some algebra here. I'm going to write it so it looks a little bit better. Or a little wonky, actually. 3 to the 4 n minus 1, and that 4 is out here. I know it looks a little wonky. Actually, I'm going to do times 1 on top, because that's fine. You don't have to do the times 1. I just looked a little off place when I put it off to the side, which is really 1/4 times 3 to the n minus 1 over 4 to the n minus 1. Guys, you do not have to show all these steps. I am not quite sure where everyone is in the class because it's an online class. So I am showing a ridiculous amount of steps just so hopefully I catch everybody in this process. So we have the summation of 1/4, 3 over 4 to the n minus 1. Okay, since they are to the same power, we can throw them in the same bubble. If you can go from here to here, that is perfectly fine. You can do it. I don't mind. However, if you need to take extra steps, do it. Don't try and skip steps because you think you can do it in your head. If you need the steps, do the steps. All right. So now we have our series in this form, a times r to the n minus 1. So I'm going to write this beside here. Oh, I'll go below. So the three things Katie wants to see on the test. 1, we use the geometric series test. METR. I do not want to spell that correctly today, apparently. So this is a geometric series. 2, my A is 1/4. My R is 3/4. The absolute value of R is the absolute value of 3/4, which is less than 1. If you're not sure, if you're looking at a fraction, if it's less than 1 or not. I know some of you online are laughing at that, but we've all been there. So we have in your calculator 3 divided by 4. Is it a decimal? Yes. Is it less than 1? Yes. All right. So that is less than 1. So our series converges. If you don't like this bullet point style and you want to write a series, or not a series, a sentence, you can say, okay, A equals 1/4, R equals 4/3, R, the absolute value of R is 3/4, which is less than 1. By the geometric series test, the sum, oh, I forgot to write my summation again. The series, the summation of n equaling 1 to infinity of 3 to the n minus 1 over 4 to the n converges. So just some bullet points of what in the world is going on. All right. So continuing on, go ahead and pause the video and try to do B and C. All right. Welcome back. So B says the summation of n equal 1 to infinity of 4 to the n plus 3 divided by 5 to the n. Does this series converge or diverge? So we need to do some work. Because I have a number raised to some power of n, I need to use a geometric series, or I think I'm going to use a geometric series. All right, so because I want to try a geometric series, the top is 4 to the n plus 3. So if I pull out a 4, I get 4 to the n plus 2. Another 4 gives me 4 to the n plus 1. Another 4 gives me n. Another 4 gives me n minus 1, which is what I want. The 4 to the n minus 1. So we had to remove 4 of the 4s to get this to be n minus 1. And the bottom, we have 5 to the n. So if I pluck out a 5, what's left over is 5 to the n minus 1. Okay, so again, doing a lot more in one whack or in one step. If you need to do it piece by piece, do it piece by piece. The algebra is actually where I see most students mess up on these problems. Okay, so we have 4 times 4 times 4 times 4. I'm not even going to pretend to know what that is in my head. So 4 to the 4th power is 256. So I get the summation of 256 divided by 5 times 4/5 to the n minus 1. So 256 divided by 5. Do I even want to do this? Let's find out. We're going to leave it as 256. So we have it in that geometric series form. A times r to the n minus 1. My A is 256 divided by 5. Let's go ahead and write our conclusion, since I'm running out of space here. So 1, we used a geometric series. 2, A is 256 divided by 5. R is 4/5. 3, I want to write a conclusion here. I've been writing these differently than I have in my past semesters. That's why I'm writing so awkwardly. Absolute value of R is still 4/5, which is less than 1. So the summation of 4 to the n plus 3 over 5 to the n converges. Guys, on the test, I typically, even if a problem doesn't require much space, we'll give you an entire page to do one of these problems, just so you have the space if you need it. Okay, so this one converges. All right, so let's look at C. We've got some different kind of algebra things going on here. We have the summation of n equal 1 to infinity of -9 to the n plus 1 divided by 2 to the 3n. All right, we got to do some work here. So first off, I need this to be n minus, I need that power to be n minus 1. And same thing here with 2 to the 3. We're going to do this in a few more steps than what we have been. So the summation, if I bring out 1, -9, I get -9 to the n power. I need that to be n minus 1. So I need to bring out one more -9. So now I have -9 to the n minus 1 power. 2 to the 3n, I can rewrite this as 2 cubed to the n. So kind of rewriting this, 2 cubed is 8. So I'm going to rewrite this as the summation. -9 times -9 is 81. So 81 times -9 to the n minus 1 divided by 2 cubed is 8 to the n. Okay, so our numerator is to that n minus 1. Our denominator is just raised to the n, and I need it to be to the n minus 1. So I need to pull one of those out. So I'm going to do the summation of 81 times 9 to the n minus 1 over 8 times 8 to the n minus 1. Oh, that's -9. There we go. So we get the summation of 81 over 8 times -9 over 8 to the n minus 1. Okay, so now we can write our Conclusion 1, this was a geometric series. And I know that because we have an actual number, raised to a variable. So our n is in the power. So number, variable. Running out of room. So this was a geometric series test that we use. 2, our A equals 81 over 8. R, the absolute value of R, equals the absolute value of 9/8, which is just 9/8. Okay, if you were not sure, 9 divided by 8 is 1.125. That is larger than 1. So that is greater than 1, which is a problem. So step 3, the summation of -9 to the n plus 1 over 2 to the 3n diverges. It gets larger and larger and larger. All right. So our last of the geometric series, we have example 2. Do the following series converge or diverge? Explain. So we have the summation of n equaling 1 to infinity, of 4 to the -2n, 9 to the n. And we want to know if this converges or diverges. Curious if our formula sheet has exponent rules. I know in my college algebra class it does. It does not. Okay. So if you guys are struggling on these exponent rules, let me know. I can send a video. I do have videos from preparatory algebra and college algebra classes explaining how these exponent rules work. And it's really all about geometric series as exponent rules. So we have the summation n equal 1 to infinity of 4 to the -2n times 9 to the n. So let's rewrite this. Remember that something with a negative exponent on top is a positive exponent on the bottom. So let's rewrite this as 9 to the n over 4 to the 2n. Just by moving this down. Now, the numerator I need to rewrite. This is going to be 9 times 9 to the n minus 1. I plucked one of those 9s out. And in the denominator, I'm going to do this in multiple steps. I get 4 squared to the n. So 4 squared is 16. And so we get the summation of 9 times 9 to the n minus 1 over 16 to the n. And so I need that 16 to the n to be n minus 1. So we have the summation of 9 over 16. So I'm pulling one of those 16s out, times 9 over 16 to the n minus 1. Okay. So here we have a perfect geometric series set up. It looks like a times r to the n minus 1. Our a is going to be 9 over 16. Our r, oh, sorry guys. I want to write the conclusion here. So step 1, this was a geometric series. How do I know this? At the very beginning, I had a number raised to a variable, raised to the n. It might be 2 to the n, it might be 3n plus 5, but a number as a base and then somewhere in the exponent an n. Now write that down. So the startings of the geometric is normally a number. So a number as the base, and then an n somewhere in the exponent. Okay, so those are your two things that you really need to have. And that's why I kind of start these off doing geometric, even though we're in the geometric series section. So one, this is a geometric series. You can't necessarily claim that until it looks like a geometric series. But when you're starting the problem, if you're looking, by the time your final gets here, you're going to be looking at all these tests going, which one do I use? And it's like, okay, which one looks like a number raised to a variable in the exponent? Nope, way too far. Okay, so geometric series. Step 2, I can prove you to that because A equals 9/16. The absolute value of R, which is 9/16, is less than 1. Again, if we're not sure, 9 divided by 16. Oops, not 163. Is 0.56. It's less than 1. So 3. So the summation, or I forgot what we were working with. 4 to the negative 2 times 9 to the n converges. There is no shame in constantly looking at this. Okay, if R is less than 1, it converges. If R is greater than 1, it diverges. Guys, your homework may ask you, what does it converge to? And if it converges to A over 1 minus R. And this is an A, not a 9. I know they run together a lot in this lesson. I apologize. So we get, for this one, we get 9/16 over 1 minus 9/16. This one's not very. So handy dandy calculator, 9/16 divided by 1 minus 9/16. Let's get a fraction for that. We get 9/7. So on the homework, on the test, I will give extra credit for this. However, it may ask it on the homework. Just a side note. I more care if it converges or diverges. Okay, one last thing before I end this video is all of ours that we looked at started at n equaling 1 to infinity, n equaling 1 to infinity, n equal 1 to infinity, n equaling 1 to infinity. Sometimes, they can start at n equaling 0. So let's say I'm going to go to another blank page. So let's say, for example, we have the summation of n equaling 0 to infinity, let's say 4 times 1/2 to the n. We're going to just do something simple. And it's asking for the sum, or does it converge or diverge? We really want to get this in the form, n minus 1. So I would just plug 0 in, and we get 4 times raised to 0, 1/2 to the negative 1, then plus the summation of n equaling 1 to infinity of 4 times 1/2 to the n minus 1. So again, whether it converges or diverges stays the same. What changes is if you're using that sum equals a over 1 minus r. So if it starts at 0, you need to be aware that you need to plug in a 0 for n, and then let your oh, why is that doing that? I don't know how to get that off of there. Sorry, guys. There it goes. So you then want to get your series started at n equals 1 to infinity. So your sum in this case would be this. So our sum for this problem would be 4 times 1/2 to negative 1 plus our a is 4 over 1 minus our r, which is 1/2. So just so you know, sometimes the summation can start at different points. All right, guys, I hope you enjoyed Geometric Series. And if you have any questions, please let me know.